Numerical solutions of nonlinear systems of equations. Introduction. The amount of pressure required to sink a large, heavy object into soft, homogeneous soil lying above a hard base soil can be predicted by the amount of pressure required to sink smaller objects in the same soil. Specifically, the amount of pressure P to sink a circular plate of radius r, a distance d in the soft soil, where the hard base soil lies a distance d greater than d below the surface, can be approximated by an equation of the form P equals K1 plus K2 times r plus K3 times r squared, where K1, K2, and K3 are constants depending on d and the consistency of the soil, but not on the radius of the plate. There are three unknown constants in this equation, so three small plates with differing radii are sunk to the same distance. This will determine the minimal size plate required to sustain a large load. The loads required for this sinkage are recorded, as shown in the accompanying figure. This produces the three nonlinear equations in the three unknowns, K1, K2, and K3. Numerical approximation methods are usually needed for solving systems of equations when the equations are nonlinear. Exercise 12 of section 10.2 concerns an application of the type described here. Solving a system of nonlinear equations is a problem that is avoided when possible, customarily by approximating the nonlinear system by a system of linear equations. When this is unsatisfactory, the problem must be tackled directly. The most straightforward approach is to adapt the methods from Chapter 2, which approximate the solutions of a single nonlinear equation in one variable, to apply when the single variable problem is replaced by a vector problem that incorporates all the variables. The principal tool in Chapter 2 was Newton's method, a technique that is generally quadratically convergent. This is the first technique we modify to solve systems of nonlinear equations. Newton's method, as modified for systems of equations, is quite costly to apply, and in section 10.3 we describe how a modified secant method can be used to obtain approximations more easily, although with a loss of the extremely rapid convergence that Newton's method can produce. Section 10.4 describes the method of steepest descent. It is only linearly convergent, but it does not require the accurate starting approximations needed for more rapidly converging techniques. It is often used to find a good initial approximation for Newton's method or one of its modifications. In section 10.5, we give an introduction to continuation methods, which use a parameter to move from a problem with an easily determined solution to the solution of the original nonlinear problem. Many of the proofs of the theoretical results in this chapter are omitted because they involve methods that are usually studied in advanced calculus. A good general reference for this material is Ortega's book entitled Numerical Analysis, a Second Course. A more complete reference is O.R.